Hello students, welcome to another video lecture on digital signal processing. In this video lecture, we will study how to design an FIR filter using window technique, and we will complete this numerical within 8 minutes. The numerical reads as: obtain the coefficients of an FIR filter to meet the specification given below using window method. Passband edge frequency 1.5 kHz, stopband edge frequency 2 kHz, minimum stopband attenuation 50 dB, sampling frequency 8 kHz. The passband and stopband frequencies are given in Hertz. Therefore, we convert these frequencies to radians per second by multiplying these frequencies by 2 pi. Therefore, we multiply omega p by 2 pi and omega s by 2 pi. Also mentioned in the question, stopband attenuation alpha s as 50 dB. Next, we need to convert the analog specification into digital specification using the formula omega equals omega multiplied by t. T equals 1 divided by 8 kHz. Therefore, we get omega p as 0.375 pi radians and omega s as 0.5 pi radians. Now, the step 1 to design a FIR filter using window technique is to select a window type such that the stopband attenuation of the selected window exceeds the given stopband attenuation. In the question, they have mentioned the stopband attenuation should be a minimum of 50 dB, and therefore we select Hamming window to design FIR filter. The Hamming window has a minimum attenuation of 53 dB, and in the question we are required to have minimum attenuation of 50 dB. Therefore, we select Hamming window to design this FIR filter. Step 2. Step 2 is to determine the number of coefficients n, and the formula for n is as displayed on the screen. The value of k depends on the window type which we are using. For Hamming window, value of k equals 4. Next, delta omega, which equals omega s minus omega p. Now we will substitute value of k and delta omega in this equation, and after substituting and simplifying we get value of n greater than or equal to 64. We will choose n as 65 so that alpha, which equals n minus 1 by 2, becomes an integer. Step 3. Step 3 is to specify the ideal or the desired frequency response, Hd of omega. Hd of omega is given as e raised to minus j omega alpha for magnitude of omega less than omega c and 0 for magnitude of omega in between omega c and pi. Step 4. We have to obtain impulse response Hd of n for two cases, that is for the case n not equals alpha and for the case n equals alpha. The formula to compute Hd of n for both the cases is as displayed on the screen. Step 5. We compute value of omega c and alpha. Omega c equals omega p plus delta omega by 2. After simplifying, we get value of omega c as 0.4375 pi radians and alpha equals n minus 1 divided by 2, and we have computed value of n in the previous step as 65. 65 minus 1 divided by 2 becomes 32. Therefore, value of alpha is 32. Step 6. We find the impulse response h of n. The impulse response h of n is given as h of n equals hd of n multiplied by the window function, and the current numerical we are using the Hamming window. Using the formula discussed in step 4, we write hd of n for two cases, that is n not equals alpha and n equals alpha. So we get hd of n as sine 0.4375 pi n minus 32 divided by pi n minus 32 for n not equals 32, and we get hd of n as 0.4375 for n equals 32. After computing hd of n, now let us write the window function. In this numerical we'll be using Hamming window, and the function for Hamming window is defined as 0.54 minus 0.46 cos 2 pi n divided by n minus 1. Now in this step we need to tabulate the value of hd of n, the window function, and also compute h of n. To tabulate hd of n, we need to substitute value of small n from 0 to 64 in the equation which we have obtained in the previous step. And for the case of small n equals 32, we already have the value of hd of n mentioned in the previous step. Kindly bear in mind, while calculating value of hd of n as well as the window function, keep the calculator in the radian mode. It is required to tabulate value of hd of n, the window function, and h of n for all the values of n, that is from n equals 0 to 64. However, you can see there is a symmetry. H of 0 equals h of 64. Similarly, h of 1 equals h of 63. H of 2 equals h of 62, and so on.